Okay, so I just emailed you your assignment for the weekend, and I'm going to now walk you through that process. So the idea here is how do I use that information from all those different kinds of graphs I showed you on Monday? How do I actually use that to figure out where the sound's going to go, on the seats where my audiences are going to be? So we're just going to dive right in here and do this. So what you might find is that I'm going to pick a loudspeaker here. And I sent you a zip file link that has all these different polar plots. And I mean, you can go out and look on websites of manufacturers and get your own polar plots for other things that you want to try. But I gave you some you can work with if you want. But this is one of them from Electro Voice. And let's just look at the specs of this thing here. So it says it has a horizontal coverage of 60 degrees and a vertical coverage of 60 degrees, which of course we know is, well, it's an oversimplification. It's far more complicated than that. In fact, if you start looking at the graphs, you would see, oops, hang on, that there's its beam width plot. It is certainly not consistently 60 degrees across the frequency spectrum because, 20, 30, 40, 50, that's 60. Where is it actually 60 degrees by 60? Only at that frequency. Yeah. Everywhere else it's something else. So, however, it is reasonably consistent directivity between 1500 hertz and 8 or 9K, which is nice. Here's the polar plots. Okay. Now, what they've elected to do here is superimpose several frequencies on top of one graph, just so that they don't have to do as many pages here. So let's take a look at. I'm going to look at the 1000 hertz vertical. So let's say someone handed us this loudspeaker and said, you have to use this as the center cluster in Stevens Center. Okay. So we need to find out if this is doable, what we can do with this. We have to make it work. So if we go, here's the Stevens Center. If you're going to hang your own little cluster, it's usually going to go right around here because there's a truss that you can hang right here. Right there between that line. So I'm going to drop a point there. And we're going to say that's where I'm going to hang this thing. Okay. What I want to know now is, if I hang this thing there, how loud is it going to be at all the seats? Okay. So let's figure out where we're going to measure. For purposes of our demonstration today, we're going to pretend the balcony isn't there. Okay. We're going to pretend that we're just worried about the orchestra area. Okay. Because the balcony makes things more complicated than I think we're ready for. So what I want to do is I want to pick some spots here along the audience area that I can use as reference points. You're not going to figure this out for every little seat. It'll take you too long. You're going to pick a few representative locations and assume that everything, if those will all work, then it should work everywhere in between is kind of the idea. So certainly, certainly the front row and the back row, and and maybe some other places in between. So let's start by just figuring out, all right, let me plop some points here, one at the front row, and I'm going to put that 4 feet up. That's about where people's ears are when they're sitting in a chair. And I'll do one in the back row as well. Okay. Now what I want to do is I'm just going to draw a line from here to there. And now I'll draw another line from here to there. Okay? Now, the question I have is, okay, if that's the area I have to cover, how wide of an area is that vertically? We know this thing is spec'd at 60 degrees vertical. So is this even feasible? So I'm going to just measure that angle real quick. Let's see what we've got here. It says 48 degrees. Okay, and this is spec'd as a 60-degree vertical loudspeaker. So, you know, probably work. It's not an unreasonable request. What we should figure out is it actually going to do it? So given that information, we know this is a 60-degree vertical. We know we're looking at covering a 48-degree or so, 50-degree area vertically. You know, we have to now figure out where we're going to point this thing. And perhaps you might think, reasonably so, that maybe we just aim it here towards the middle. If we aim it there, and it's a 60-degree-ish vertical, then, you know, we've got enough on either side there to cover that area. So let's see what happens there. So here's what we're going to do. I'm going to label these seats, okay? So this will be, oops, hang on, I want that one.
Jason, just so I can pull the data sheet, which loudspeaker are you talking about?
It's the FRI 122 something or other.
Yeah.
So, yeah.
Just a quick question. I might be either getting ahead or completely missing the mark here. So say this loudspeaker was a 90-degree loudspeaker, right? Would you put the focus point at the very back, since it is a 45-degree angle already, and then you would have no sound going past your first point, and then only sound going out towards the back of the house?
You're getting the point, but you're also ever so slightly ahead of me. So give me a moment here, and then we'll examine some of this. So I'm going to call these seats A, B, and C. Now, I'm going to be generating a lot of numbers in this process, and I would rather not have to remember all of them. So I'm going to use Excel to help me remember these things, okay? So I'm going to say seat A, seat B, seat C. I don't want you to obsess over what I'm about to do in Excel. Excel is not the point of this. It's just the thing I'm using to keep track of the math, okay? So the first little bit of information I want to know is the distance from the loudspeaker to each of these seats, because that's going to affect how loud things are. We know that, right? Before we even learned about that there was a thing in directivity, we learned that there was a thing called distance, and the distance affects how loud things get. So that's the first thing I want to know is how far away are these things? So let's see. Distance to seat A is 33 feet 2 inches. I'm just going to say 33 feet. Now, 2 inches is probably not super important from a loudness point of view. Distance to seat B, 50 feet 2 inches. So 50 feet. Distance to seat C is 76 feet 9 inches. So I'm going to call that 76.75 feet, okay? That's how far we are. Yeah? So now what I'd like to find out is if I'm saying B is where I'm aiming this thing, B is therefore where it would be the loudest, just naturally, right? Based on what we know about directivity. Yes? So I will call B 0 dB. So I'm going to put a 0 here, and I'm going to call this row dB loss over distance. And I'm just going to, we know we will lose some amount going to B. What I'm interested in is how much more do I lose at the other seats compared to B, because B is my theoretical highest point, right? So given that C is now 76.75 feet away, let's do that math real quick. what would be the dB difference between something that has traveled 50 feet and something that has traveled 76.75 feet? So I would just do 50 divided by 76.75 log 10 times 20. So seat C will be minus 3.7 dB quieter. Okay? Just because it has to travel a little bit farther. Okay? Now what?
Seriously, like math still works that way?
Yeah. It hasn't changed since I taught it to you.
No, but I mean it's like the math that we have been doing is moving across one axis.
Yeah.
The addition of the angle doesn't change.
Well, we haven't looked at the angle yet.
Oh.
We're not talking about angle. I'm just talking about distance. These seats are all a different distance from this loudspeaker.
But it's not as though we are sitting at B and then moving along that same axis back. Like we are doing elevation change and we are looking at a different direction.
But at the moment we're just looking at center line. We're assuming everyone's sitting in the center of the room, and therefore I'm just measuring the actual distance from the loudspeaker to the seat. Altitude is not yet relevant. It's just distance, right? How far away are you from the thing? Now, the fact that you went up affected how far away you were, right?
Yeah.
So, all right, so what about this other one? We're going to do 50 divided by 33 log 10 times 20. All right, this one is 3.6 dB louder. Seat A is 3.6 dB louder because it's just closer, right? Sound didn't have to go so far, so I didn't lose as much. Okay? So now what I'd like to know is if B is my theoretical on-axis reference point, how much do I lose by going off-axis to the front row or the back row? Because at the same time that I am changing my distance, I am also changing my angular relationship to the loudspeaker. Okay? And we know when you change angles, the sound changes. Look at the polar plot and it'll tell you that, right? As I go downward from on axis, this 1 kilohertz gets quieter. As I go upwards on axis, 1 kilohertz gets quieter. Okay? The question is by how much and at what angles. So the first thing I want to do is here I will say angle from axis. So this is, vertical angle, I'll just say. Let me just call that vertical angle. So this is like how far off am I from the axis? Well, in this case, B is 0 because that's where I pointed it, right? But what about A? Well, if I measure this angle between B and A, it is 33 degrees. Okay? What about A to C, B to C? (15 degrees). So what I'm going to do is actually, I'm going to call this negative 33 because I went down. All right, so the question now is angular loss. How much sound am I going to lose by going to these angles?
Does the math work the same way there? Oh wait. No,
We just look at the plot and see.
I thought you were just going to do like Pythagorean Theorem.
We're going to get to that in a minute here. So 33 degrees would be about here, right? Now the question is, how much do I lose at each of these lines?
6 dB.
Is that what it says at the bottom?
Wait, watch me do right.
6 dB per division. You are right. So at 33 degrees, I am about halfway between the on-axis line and the 6 dB down, right? On this orange line. The orange line is the 1 kilohertz I'm looking at. I am about halfway. So I'm going to say that's minus 3 dB. Okay? So
Are you looking at 1K right now?
yeah. So I'm just saying at 1K, I'm going to lose 3 dB going off-axis to the front row. Okay? See that? Now, at seat B, I have no angular loss because I'm on axis. What about seat C? I'm going up 15 degrees. So I go here, I go up 15 degrees. That's about halfway between 0 and 30. Oh, look at that. There's that huge dip there. I am probably, it's not quite 12, but I'm going to say 10. So I'm minus 10 there. Okay, so now I just have to total this up. So what is 3.6 minus 3? I get 0.6. Here I'm at 0. At the back row, I'm at negative 3.7 plus negative 10. Oops, what did I do?
Negative 13.7.
Oh, yeah, so plus 10. So negative 13.7. OK, so the difference here, this is at 1 kilohertz. We would, of course, do this for all the frequencies to get a clearer picture. But at the moment, we have a difference, a pretty dramatic difference, right? So there's almost a 14 dB difference between the front row and back row. That is outside of that 6 dB window that we're usually comfortable with. Okay? So this thing that I thought was going to be no big whoop is a whoop, right? So let's take a look at what's going on here. So,
Sorry, real fast for A, you're adding the dB loss over distance to angular loss, right?
yeah.
So why are you at 0.6?
Well, because I got a boost because I'm closer, but then I got a loss because I went off axis. So here I had a positive number, I had a gain, and then I had a loss. So I ended up with only 0.6. Whereas here I had 2 losses. Okay? So let's take a look at what's going on here. Well, one thing that's happening here is I have this weird dip on that vertical thing of the loudspeaker. And that's only happening at 1K. It's not happening anywhere else. I guess it's happening a little bit at...
So pick a better frequency.
Yeah, pick a better frequency. But part of what's going on here is that because this is one of those loudspeakers that has like a horn and then a thing underneath of it, a low driver underneath of it, every time you have that, whatever frequency is half a wavelength from the distance between the two centers of those drivers is always going to have a little cancellation on that vertical angle, okay, when those distances line up at half a wavelength.
Would it be stupid? It probably would be, but would it be stupid to turn the entire cabinet 90 degrees?
Well,
Equal dispersion.
in this case, maybe. But what's going on there is that I bet you the crossover point is somewhere around 1 kilohertz on this thing. So both drivers are putting out 1 kilohertz, and then they're spaced 6 inches apart or so. And so you go slightly off axis, and you get that cancellation. So we could, let's just say that we're going to find a solution to that, like maybe rotate it around or flip it upside down or something so we don't have that problem. So let's pretend that that dip didn't happen. Where do you think the sound would be at 15 degrees? It would be about -6. Right? So even if I say, okay, it's not -10, it's actually -6, now what's my loss? Right? I'm still more than my 6 dB window that I would like to be. Okay? All right. So here's the other thing that's going on here. The reason that we are getting hit so hard at the back row is that we're taking a loss twice. We're taking a loss because it's farther away distance-wise, and we're also taking a loss because it's off axis. The reason that the front row is functionally the same is that we have a gain by virtue of getting closer, and that gain is offset by virtue of going off axis enough that generates the same amount of loss, or the opposite amount of loss to what we gained, and it zeroes out. Okay? So hopefully you're starting to see that relationship between distance and the directivity. Sometimes it can hurt you, and sometimes it can help you. What could we do to this scenario to leverage this in a way so that it's never hurting us? This is one of these strategies that absolutely separates the amateurs from the professionals. Okay? The amateurs will always aim the loudspeaker at the middle of the seating area. And it's not an unreasonable conclusion to make, right? I mean, we walked through that thought process of, oh, it's a 60-degree vertical horn. I've got about a 50-degree area to cover. I will point it at the middle, and it will cover the area, right? That is not an unreasonable conclusion to draw. The problem there is we weren't considering all the variables there. we weren't considering the fact that even though that 50-degree area is less than the coverage of the horn, we have a pretty dramatic difference in distance between, one side of that angle and the other side of that angle. And that difference in distance makes a huge difference in the amount of sound we end up with, okay? So the amateurs will always aim it at the middle. The professionals will always aim it at the back row. Why? Because remember, the back row is killing us here because we're taking a loss twice. We're taking a loss over distance, and we're taking a directivity loss. Wouldn't it be great if we could not have one of those? Right? We can't ever get away from that distance loss, right? Because we can't make the back row be closer, right? Other than maybe move the loudspeaker, but so far that's not an option to us. We have the truss. That's where we have to hang it. So we can't make the back row move closer, but we can certainly eliminate that directivity loss by pointing that loudspeaker at the back row. So if the back row is the on-axis point, then we have no directivity loss to the back row. Does that make sense? So let's change this now. So now I can't get rid of that minus 3.7 for the loss, but I can certainly change this angle. So this becomes 0 now. And now B becomes an angle of 15 degrees. I guess I already knew that. Minus 15. And this is still 33, right? So that, oh, wait, no, it would be 33 plus 15, right? Yeah. So we're looking at 48, minus 48 degrees. OK, so I have no angular loss now at C, because I'm not.
Wouldn't your dB loss change too? Because isn't C the new 0? And then
Yeah, you're right. We should probably do that. So if I say that's my reference point now, then I could. It would be that same amount, same loss, but let's go ahead and try it. So we would do 76.75 divided by 50 log 10 times 20. So we do a 3.7 gain here because we're closer, right? Then here, this would be 76.75 divided by 33 log 10 times 20. So we're actually doing a 7.3 dB gain now, right? OK, so we get 0 loss of directivity at seat C, but we certainly are going to have some angular loss. Let's take a look. If we go over here, minus 15, how much have we lost? Maybe a dB?
Call it 2. Why not?
Well, I don't think it's quite 2. I'm going to say 1. I'm going to say 1. I'm going to say 1. And then we're going to minus 48 to seat A. And where's that? So 40, 50, it'd be right around here. It'd be right around that 6 dB point. So 6 or 7 dB, right? So I'm going to say it's minus 7 dB. OK, so now what's the difference here? No difference there. But now I'm looking at 2.7 at seat B and 0.3 or negative 0.3 at seat A. Look at that. Now I'm within a 3 dB range in that entire area. So why does that work? Because I'm aiming on axis to the back row. And so as I go off axis and get closer to the stage, 2 things are happening. One is I'm getting closer to the loudspeaker, so it's getting louder. But I'm also getting off axis, and therefore it's getting quieter. So it's going, staying even, right? So as I'm gaining level by getting closer, I'm losing level by going off axis. And it balances out. It's like a little scale. Your question?
My question was, so in the case of our number 1, right? He was between 1 or 2, from Nora's point of view. He chose 1.
It's 2.
And then it was 6 or 7 from your point of view, and you chose 7. So are you usually trying to I understand that it doesn't really matter. It's just a single dB.
Yeah, I just try to get as close as I think it is. If it's a difference of a difference of 1 dB does usually not make or break this scenario, right?
So if it's a difference of like 6 to 7 dB, you see what I mean? Does it still not make or break the system?
It's you know. I mean, it boils down to, can you hear it?
All right, fair enough.
Right? Can you hear the difference between -6 and -7? Probably not. Can you hear the difference between -1 and -7?
Yes.
Yeah. Right? So you just have to pick your battles. I mean, you're never going to get it perfect. This is not perfect. Not every seed is the same loudness here, but it's within 3 dB. It's within that window that most average people would not be able to notice the difference. Okay? All right. So now let's introduce the horizontal axis. Everybody with me so far on that? You got that? I really hope you're paying attention because you're going to have to do this weekend, and it is not going to make anywhere near the amount of sense that it's making to you right now, because I'm going to make this look really easy. So I really, really hope that you are paying attention. We'll see.
This is the week that the video doesn't upload.
All right. So let's take a look at another theater. So let's look at DeMille. I want to look at DeMille because it's kind of weird. Okay, so here's DeMille. Let's take a look here. I've got the ground plan of the section view. Now, in DeMille, anybody know what we have hanging up in the air in there? Yeah, so we have this loudspeaker called a KF300. Here it is in all its glory. So this thing is spec'd 90-degree horizontal, 50-degree vertical, which again is a way oversimplification. But what we need to do is find the polar plots. Here's polar plots, and they've got them for every frequency. Well, every octave band. And then they go third octaves down here. So let's start with the vertical, because we know how to do that. And I'll start at 1K.
Hey, Jason.
Yeah.
Quick question, kind of backtracking a little bit. When you are aiming this, are you aiming like, so that had the full range over and then like a tweeter or something, right? Are you aiming at like in between those two, at like the center of gravity, or are you aiming at like at
The horn is the part that's directional. So that's the part you aim.
Okay, gotcha.
Right? The low frequency is not directional. So.
Yeah. Okay.
All right. So let's take a look here and see what we can do. I'm going to do the same basic process. We're going to assume for now that the pit cover is in and we've got those seats there. So we'll do a seat right there. Oh, I got to change my point style. Let's do. There we go. Okay, so there's a point there, and I'm going to put one at the back row, which is here. And where do you think the middle row is? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 8, 7, 6, 5. We'll do it there.
Okay.
Oops. All right. This will be seat A. And B and C. Okay, so I'm going to use my same spreadsheet here and just repopulate the numbers. All right? Clear contents. I am going to aim this thing at the back row because that's what professionals do. And you are a professional now. This loudspeaker is hung right about here. And I would think the horn is actually somewhere there. All right? So let me draw my reference lines here. One to there. One to there. One to there. OK, so what are my distances? Distance to C is 38 feet, 5 3/30 of an inch. So I'm going to call that 38.5 feet. Oops, C. 38.5 feet. Can anybody have violent objections to that assessment? Seat B is 28 feet, 10 inches. I'm just going to call that 29 feet. OK. Seat A is 21.9 and 21/32 inches. I'm going to call that 21.75 feet. OK? So loss over distance, we're going to say 0 at seat C, just because that's my reference point. And then let's see what we end up with here. So at seat B, 38.5 divided by 29, log 10 times 20, we get a gain of 2.46 dB. So 2.46. Now what about the front row? We're going to end up 38.5 divided by 21.75. Log 10 times 20, I get 4.96 dB. I'm going to call that 5. OK?
Oh, and those are positive numbers, right?
At the moment, yes, because we're gaining because we're getting shorter, right? And just to simplify my math, I'm going to call this one 2.5 because we're sound people. We like small numbers. Let me save this here just so that I've got it. OK. So let's take a look at angles now.
So just knowing the fact that the dB5 for A, would that already tell you that you might want to go down with your aim point a little bit?
No, this is normal.
Oh, OK.
Right? The whole point is the front row is louder because it's closer.
Yeah.
Right?
Yeah, but because it's going to be like when you do the vertical, or I guess in this case the horizontal angle, because if we're doing the vertical angle loss. Am I crazy?
Well, if I do, the reason I'm aiming at the back row is so that when I go off axis to the front row, the loudspeaker gets quieter. At the same time, it's getting louder because I got closer.
Oh, OK.
Right?
Yeah.
So you have to think three-dimensionally here on this thing. This thing is still clipping a little bit. Let me turn that down. OK. All right. So vertical angle, I'm going to say 0 for seat C. Let's take a look at the angle here. Angle to B is 18 degrees. I'm going to say minus 18. So I know I'm going down. Angle to seat A is 42 degrees. Negative 42 degrees. OK? So angular loss at seat C is 0. Angular loss at seat B, let's take a look at 18 degrees. Vertical off axis. That's going to be somewhere in this area. Looks like it's 6 dB per division here as well. They've got them actually labeled here. See that? So I think it looks like about minus 2. So I'll put a minus 2 in there. Now what about to the front row? The front row was negative 42 degrees. So that's going to be somewhere in this area. Looks like I'm maybe minus 3 there. Yeah? All right. Great, I'm good, right? Let's see what the total is. We've got, we're going to end up with a +2 at seat A. We're going to end up with a +0.5 at seat B and a 0 at seat C. We're within 3 dB. That's pretty great, okay? That's vertical. Let's look at horizontal now. So I'm going to, we have to figure out where these seats show up in the ground plan. So I'm going to use some construction lines here to figure that out. So here they are. So I'm going to plop those points in right now. So that's seat C. That's seat B. That's seat A. Okay? You understand how I did that? This is why I really like having a file that has both the ground plane and the section lined up like this. Makes it a lot easier to traverse it and figure out the adjacencies.
What's the construction line on the
X line. Yeah. It's just it's an infinite line.
Yeah.
You just draw it and it goes on forever. It's a good way to like see where things intersect and stuff. Okay, so let me copy my labels over here. Oops. Oops, I copied the wrong thing. Put one there, put one there, put one there. So this will be B. This will be C. Okay, so why am I going to so much trouble to find these same spots on the ground plan? Because I don't want to have to do the vertical loss math more than once. Okay, so I'm going to try to figure out horizontally what's going on here, and I want the vertical loss to stay the same, which means when I do horizontal measurements, I want to make sure I'm doing it on the same three vertical rows, so I don't have to do this math more, because we're sound people and we don't like to do more math than we have to. So I'm going to minimize this math. So I'm going to pick some seats on these same rows that are horizontally significant. So maybe here at the front row, I'll do one, what, there, maybe? It's probably the farthest anyone's going to sit. At the back row, maybe that's probably the last seat on that back row, right? There probably isn't one right there. So I'll put one there. And then I'll put one, let's see, last seat would probably be there. You agree? Yeah. Okay. So let's label these now. Now the good news is this loudspeaker appears to be symmetrical for the most part. So I'm only going to really worry about this side. I don't have to do the other side. Usually it's the same. If the room is symmetrical and the loudspeaker is symmetrical, usually you figure out one side and the other side will be the same. Grayson, you had a question?
Yeah, so if you're doing it like, so say a room has like, or it's really wonky and it's like, 10 feet over. So you have one side that's further away from the stage and the other side that's not.
Well, then you got to plot this on both sides to figure it out. You got more work to do. Okay, D, E, and F. Okay, so I know that D is going to have the same vertical angle and the same vertical loss because it's in the same row. So I'm going to change this to vertical angular loss. And I know that E is going to have the same vertical angle and vertical loss as F is going to have the same as C. So this will be -2. Okay? Now, what about the distance?
So I have a question.
Yeah.
You're assuming that all these rows are straight.
No.
Because
I'm assuming they're flat.
flat, because vertical loss.
Yeah.
Okay.
Right? Whether I'm sitting here or here, I am still the same height up in the air.
You are, but you're a closer distance.
Right, which is exactly what I want to talk about right now.
So vertically, like your vertical loss by moving closer.
Yes, okay, but we don't have directivity data for that angle. All we have is vertical, horizontal.
Okay.
So yes, in real life, now we're looking at a cross-section that goes diagonally across the loudspeaker, but we don't have data for that. So all we can do is try to interpolate the horizontal and vertical data we have.
Yeah.
And in real life, our estimations in that case are going to be worse than reality because, yes, there's probably somewhere in between that it probably does a little conical thing. But we don't have that data. We can only work with the information we have. But this is why, we ended up now we do this more with computers because the computers can figure out that angle that we don't have, right? Okay, but the question is, what is the distance to seat D, E, and F from the loudspeaker? I don't know is the right question, or the right answer. So where is the loudspeaker? It is right here, right? But the distance to seat D is not the distance of that line, 18 feet 6 inches. Why?
Because it goes up.
Yeah, because there's a vertical issue here that is not accounted for in the ground plan. So this is where we have to do a little bit of triangle math. Okay? Anybody guess how we could figure out this distance?
No, you have both of your distances.
You all took way more math than I did in high school, so tell me how to do this.
So easy. What's our distance vertical?
Yeah,
Vertical distance.
Pythagorean Theorem. So here's what I'm going to do.
So not
I'm going to... So line A of my triangle is this one from the ground plan, right? Line B, if I do a construction line horizontally on the section from seat A, then B is that distance, right? From the point to that intersection of that line, right?
Yeah. Shouldn't it be to?
So you just need the height of the loudspeaker and the distance from the
Yeah.
Yeah, but it's the height of the loudspeaker
To
from
the seat.
the seat, right? Not from the floor,
Stage.
right? So it's the intersection of these two lines. That's B, right? So side A of my triangle is this line I got from the ground plan. Side B of my triangle is this line I get here. So what are these two things? So part A of my triangle is 18.5. So let me insert some rows here. Okay, so A was what?
18, I think.
18.5. B is 17 foot 3 inches, so 17.25. Okay, so let's figure this out. I do 18.5 squared and 17.25 squared and sum those together into my memory here. I get 639.8125. And then I'm going to bring that back in, and I'm going to take the square root of that, and I will get 25.29 feet. That is the distance to seat, make sure, D. Yep. So 25.29. Okay? So that is actually the distance. Oops, I put it in the wrong spot, didn't I? So this is the distance. So let's figure out the distance to E, shall we? Yes, Jason.
That was a great commercial.
Okay, so my A is 30 feet 9 inches, so 30.75. My B is going to be 13 feet 6 inches, so 13.5 feet. Anybody do that math? On those two numbers? 30 points, oops.
Jason?
Yes?
The A-leg for E was 30.75, correct?
Yes.
Oh, sweet.
13.5 x squared plus recall. Oh, no. Square root. I got 33.58 feet. Anybody else get that? Anybody? Yeah, am I right? 33.58? Okay. So 33.58, that is the invisible line. 33.58 is the distance to E. Now what about the distance to F? Well, let's see. Let me draw a line first. And then let's measure that. "37 foot 10 inches. I'm going to call that 38 feet. Okay. B in this case is going to be a fairly small number. "6 feet 11 inches. I'm going to call that 7 feet. Okay, so what's my distance? 38 squared plus 7 squared, and the square root of that, I got 38.64 feet. Okay, so there's my distance. Okay, so now I just have to figure out what do I lose or gain going to those seats as compared to the back row center. Yes? So we'll do 38.5 as the distance to the back row, divided by 25.29, which is the distance to off side of front row, log 10 times 20. I'm gaining 3.65 dB.
So going from point C to point D?
Yeah, because C is my reference. That's where the loudspeaker is aimed, right? So I compare everything against that. So I'm going to insert. Well, actually, I can do it here. So I am gaining 3.6 dB because of distance to seat D. What about to seat E? 38.5 divided by 33.58. Log 10 times 20, I am gaining 1.19 dB. Because I'm a little bit closer. Okay. What about to seat F? 38.5 divided by 38.64. It's not going to be much. 0.03 dB. I'm going to say that's nothing. I'm going to say that's still 0 for loss over distance. Okay? So now we can do the angle. We know that that angle is 0 for there. Vertical angle loss is nothing there. But now I need to figure out horizontal angle loss. So horizontal angle. And insert another one. Horizontal angle, angular loss. So first, what are the horizontal angles? They are 0 for A, B, and C, right? Because they are on the center line. But D, on the other hand, is going to be something different. So what is that angle? Let's find out. $57 degrees.
Which point is your?
Oh, sorry, I measured off of F.
Right.
Good catch. We'll do it here to there. 73 degrees. Good catch, Lance. Okay, let's try that again. Well, we'll do seat E. Now we're at 64 degrees there. And seat F, which will be 16 degrees. Okay, so let's figure out the horizontal loss for those. Here I am at vertical polar data. I want horizontal. Horizontal 1 kilohertz. There it is. So my first angle is 73. So here's 60. 70 would be about here. Oh, look at that. It's right at the 12 dB down point. So we're going to be minus 12.
Well, what's your 0 at? Your 0's at 6, so you would only take. No, it's at 0.
It's at 0.
It's just marked
here.
differently.
Yeah.
Okay, it's just marked release range.
Yeah, there's no standard for these polar plots. Everyone does them a little different. Okay, so now 64 would be about here. So I'm what? What do you think? 9 minus 9? 10 maybe?
Which is each point? Which is each division?
6 dB per division. Here I'm 16 degrees. That's going to be about here. Maybe I'm minus 2 there. Okay, so what's the total? So 3 point. Let me highlight the rows that are meaningful to us right now. Okay, so what's the total? 3.6, negative 3, and negative 12.
3.6, -3.
Negative 12.
12.6.
So we are negative 12.6, right?
Yeah, -12.6. Yeah.
Is that right? What about this one? 1.19 minus 2 and minus 9. Oops. Yeah, negative 9.81.
Give me the third one. It's -2.
Third one is 0, 0, and negative 2.
-2.
Okay, so this is our range.
The first one is actually negative 11.4.
Correct.
Excuse me?
Because negative 15 minus 3.6.
Yeah.
Oh, my negatives.
Okay, so there's our range. I'm going to call this not acceptable. Because we have a difference of between 0 and negative 11.4. I would like that to be no more than 6 dB range. Okay, so and I said that this is what we have hung in DeMille, right? And this is what it's doing. Why would we allow that to happen if this is what's happening?
You can put fills in.
But we don't have fills. It's because there's 2 of them, right? So here's what's happening. And we don't have to to go through this because it's not something Lance is going to have to do this,
Yeah.
but the rest of you are not.
Suck to be a grad student.
That's great.
Let me change my camera view here. Okay. So what you're going to do is if you can figure out so let's look at the polar plot again horizontally. And let's figure out where it drops 6 dB, at what angle it drops 6 dB. What does that look like? 40 degrees? So what you would do is you would draw a line from here that was 40 degrees off from center line. That's where you would aim the first loudspeaker, right? Which means it would hit 6 dB down on the center line. And then you would hang another one right next to it, pointed negative 40 degrees. Okay? And then the two 6 dB down points would line up on the center line. And what happens now this is assuming you could get it perfectly time aligned. What would happen when you get two signals perfectly time aligned that sum together in the air? It would be plus 6 dB. If you can get it perfectly phase aligned, then you would get a full 6 dB. If you don't, it's 3. But if you could get it perfect, which is actually, it's possible, actually. It seems like it's not possible, but this is possible. You could actually get a full 6 dB boost at that spot where both loudspeakers are -6, which means between those two 40-degree lines, you have effectively on-axis response all the way across. And you only start taking loss when you go this way. And we know, just based on the little bit of math we've done so far, that if all we have to go is this far off axis horizontally, we're fine, right? This will more than cover this area, okay? So that's the basic strategy. When you realize that something is not quite covering it, you have to ask yourself, do I get a different one that is wider, or do I just use more of this same thing and array them in a way that gets me the coverage I'm looking for? We don't have time to get into that and do that right now, but that's something you're going to have to do because I'm going to give you probably a wider area than you're going to be able to cover with one thing. So you may have to figure that out. And later, when we learn how to do this in Ease does a lot of these measurements in math for us, and I wouldn't say it's easier, but you're able to consider a lot more data points at the same time than you can now. It's just in this method, it's really difficult to really fully wrap your head around all the variables all at the same time. You have to kind of really truncate the amount of information you're wanting to look at. So what is it that I'm asking you to do? I just sent it to you, but let's just review. So if you are not Lance, this is what you're going to do. You're going to, your assignment is to use published directivity data such as polar plots and isobars. So I've given you a link to where you can download some of that kind of stuff, but you can go out and look for others too if you want to try something different. So you're going to try to determine an appropriate center loudspeaker for the Patron's Theater. And I sent you a drawing of the Patron's Theater with a seating layout that you should use. So figure out a place to hang a loudspeaker there. And it doesn't really matter where. You hang it anywhere you want, but it maybe ought to be reasonable, given what you know about how shows tend to happen. I want you to do this at 2 kilohertz. Okay? In real life, you're going to want to look at all the frequencies. Okay? But just for reasons of keeping this simple for now, just worry about 2 kilohertz. And I want you to do this for 2 different loudspeakers at least. Okay? So plot 1 that you think might work. So just measure kind of the general area you're covering, look through those polar plots, find a loudspeaker that you think might work. Do this process, plot the points, figure out how the coverage would lay out, and then go find another one that you think might work. Put that in, plot that one too, keeping track of your data in that little Excel spreadsheet or on a Word document or however you want to keep those. I do want to see your data, so you're going to have to show that to me. And figure out which one gets you the best result, right? gets you that the lowest range of different, loudness levels at all the seats, right? And then tell me which one is the one you think you would do. So pretend like I'm hiring you to design a center cluster for this theater, okay? In your case, you won't need a cluster. You'll probably be able to just do one loudspeaker. You should be able to find one that could cover that area. No big thing, okay? So if you are a Lance, then you will have to do basically the same thing, but I'm going to make you do it for the Friedman Theater. And I gave you the drawings for that. Friedman is a lot wider of an area to cover. Probably. I mean, I think you'll see that it is possible to get one loudspeaker to cover that whole area, but it's got to be a very special kind of loudspeaker, and you've got to be able to hang it in a very specific place, which is not always possible to do. But basically the same thing, same process, just different theater. And so you may actually have to make a cluster.
Can I do it? Does it have to be a center cluster, or could I hang 3 individual points?
You could do it however you want. Okay? Just come up with at least 2 options and compare them. So that's part of the assignment is I want you to sort of like look at your own data that you generated and say, okay, which of these sets of data is better, right? Which is the more desirable scenario? And I want to. So it's not enough that you can just generate the numbers. Can you analyze those numbers and make a decision based on them? I want to see if you can do that. Okay? Because every once in a while somebody will do that. They'll say, oh, this one's better, and I'm like, no, look at the numbers. It's not. It's demonstrably not better. So I want to see that you can look at those numbers and make sense out of them. All right? Any questions?
Yeah. How do you overcome like crappy CAD drawings?
What's there to overcome?
So say you have a ground plan and a section view, but they have different measurements.
You got to scale them to make them match. You may have to turn off some layers and stuff to like hide all the crap that you don't need to see. But yeah, I mean, definitely you want to make sure if that both drawings are scaled the same way with the same origin points and all that kind of stuff. I mean, in origin points maybe not as important for this, but they will be later. Because you could just measure the distances, but they need to be scaled the same for sure. Otherwise, like if one of them is scaled in feet and the other is scaled in inches, you're going to have problems.
Another question was, we chose to do 1 kilohertz today, right?
Mm-hmm.
And maybe I just missed the reasoning because of that? As to why we did that?
So generally, there's not a whole lot of productive work that can be done with this below 1 kilohertz, just because very few loudspeakers are really very directional below 1 kilohertz, just because of the size of 1 kilohertz is about a foot wavelength, and most loudspeakers are not larger than a foot on one of their axes, so it's usually not super productive to waste a whole lot of time trying to plot directivity for much lower than that. So I usually start at 1 kilohertz. And in something like ease, I usually have you plot 500 hertz just so you can see. Here's what happens when you go below 1K. Like, whoo, opens up, right? Just so you can see what that looks like. But you're not going to spend a whole lot of time there. You're really looking at that 1 kilohertz to 4 kilohertz range is the area that you're really trying to make work.
That was going to be my question. Is like, why don't you just, if you're going to do it just the one time, why not do it in 4 kilohertz instead of 1 kilohertz? You know what I mean? But if it's just for teaching purposes.
Yeah. It was much easier for me to make the point I was trying to make at 1 kilohertz than at 4 kilohertz. But in real life, you're really looking at 1 kilohertz, 2 kilohertz, 4 kilohertz are the 3 frequencies that you're really focusing on and trying to get those dispersed really well. 500 is really just oh gee whiz, look how it went omnidirectional, right? You know, that's really all 500 hertz tells you is the difference between directional sound and not directional sound. Okay. So that you remember that below that it gets omni. Okay? I'm also, by the way, saying, no, I didn't say that. Never mind. Just worry about covering the seats for now. Okay? So this is due on Monday, and we'll go through them together. Okay? We're gonna pull them up one at a time and See what you were able to do or not do.
You want us to submit in some form? Or Corona? Should we just like?
Email it to me,
Okay.
because I don't think I've got it set up on Canvas.
Yeah.
So. We do. I just don't have it turned on. Cost is not relevant.
It's like if you were preparing it for a client,
Yeah.
you'd be like, here's the really great option, here's the budget option.
Cost is not relevant for the purposes of this assignment. I'm more interested in just your ability to compare two things. All right. Yes, in real life you probably would want to care about cost, but we're not there yet. I'm just really more interested in just can you generate two accurate sets of data and analyze them, which sounds easy, but it's harder than it seems. Okay? And yes, this is the hard way to do this, but for a long time this was the only way.